Hi, welcome to my channel. In the previous video, we discussed about the definition of decision tree and some terminals of the decision tree and the types of decision tree algorithms like ID3 algorithm, C4.5 algorithm, and CART algorithm. And also we discussed about the training and visualization of decision tree. In this video, I'm going to explain about the making the prediction with the help of a decision tree. Okay. Now in this example, we are going to use our data set is like a iris flower dataset. Iris flower dataset is one of the standardized dataset. So it contains four features like sepal length, sepal width, petal length, and petal width, and corresponding class labels are species like it contains Setosa, Versicolor, and Virginica, and each class contains 50 instances are there. Okay, each class contains 50 instances. Okay, totally we are having the 150 rows and 5 columns. The 5 columns are called as a sepal length, sepal width, petal length, and petal width. These are the features and corresponding class labels like species. So now based on this data set, we are going to train the model with the help of a decision tree classifier, and we are assigning the max depth equal to 2. Okay, max depth equal to 2, and we are going to use the model called as a CART algorithm. The CART algorithm called the default, the value of that one is criterion equal to Gini value. Based on this information, we are trained the model. Now, so this is about the decision tree. In the previous video, we discussed about how to construct the decision tree and how to visualize the decision tree. Based on that experiment, we got this type of tree structure. So this is one of the decision tree representation of the iris flower dataset. Okay, iris flower dataset. Now it contains petal length, and this is one root node. This is one root node, and this is a subroot node or intermediate node. And these are called as class leaf node 1, leaf node 2, leaf node 3, and this is called as corresponding class label Setosa, Versicolor, and Virginica. So here the max depth equal to 2 only. So this is level 0, level 1, and level 2. So this is about the overall information of the given data set. So now based on this information, we are going to make the predictions. So for example, suppose you want to find a iris flower and you want to classify it. This is our aim. Okay. Now you want to start at the root node at a depth equal to 0, and that is called as a depth equal to 0, and at the top node. Okay, this is a depth 0, and this is the root node. Okay. Now this node makes whether the flower petal length is smaller than the 2.45 centimeter or not. So we are going to check the condition. The condition is equal to petal length less than or equal to 2.45. Now if it is true, then we can move to the root node to left child of the node. Okay, that is at depth 1. We are going to left of that root node. So if the condition is true, then we are going to move the left of that root node. Okay, so we have reached some leaf node. Okay, that is a leaf node. Now this is called a leaf node, and it predicts all the class belonging to corresponding class labels, and the decision tree predicts your flower is a iris setosa. So the flower is called as a iris setosa. So here here the petal length equal to less than or equal to 2.45. So here this condition true, then the number of samples that satisfy these conditions are 50 elements are there. All the 50 elements are belonging to Setosa only. That means 50 are belonging to Setosa, and the 0 belonging to Versicolor, and 0 belonging to Virginica. Like that, we are going to keep the things. Now here, what happened? The Gini value equal to 0. That means this class contains all the elements are belonging to Setosa only. That's why this node is called as a pure node. So there is no impurity. Okay. So if based on the Gini value, we are going to find out that is a pure node. Okay. Now here, so we want to find the another flower. So here at this time, we are going to use the petal length is greater than the 2.45. That means after the condition, if the petal length is greater than the 2.45. Okay, that means its condition is false. This condition is going to be false. Then we're going to check this condition. Okay, now at this condition, you must move down the right child of this is the right child. Okay, right child of the root node, and at this is at the depth 1. Depth 1, this is depth 0, depth 2. Okay, now it is not a leaf node. This is not a leaf node. This is intermediate node. Now, so that we can ask another question: if the petal width is smaller than the 1.5 centimeter node. At this condition, what happened at depth 1? We are going to check the other condition, other attribute condition. In the previous root node, we are going to check the other attribute. In the depth 1, we are going to check the other attribute condition. Okay, here the condition equal to petal width is less than or equal to 1.75. If it is true, we are going to left side. If it is true, we are going to left side. Otherwise, we are going to right side. Okay. Now, if it is the petal width is less than or equal to 1.75, then it's true. Then we are going to okay, on the left of that root node. So then we are at the depth 2 and left of that root node. Okay, now if it is not, we are going to if it is a condition false, then we are going to the right node. Okay, at the depth 2. Okay, now it's a really simple one. So one of these many qualities of the decision tree is that they require very little data preparation. So you don't require any high level data preparation. You require, if it's a small preparation, you can get the corresponding class labels. Now, in fact, they don't require feature scaling or centering at all. Okay, that is a very important concept of the decision tree. So a node sample attribute counts how many training instances it applies to. Okay, here for example, 100 training instances at the 100 training instances have the petal length greater than or equal to 2.45 centimeters. So that means here the first root node contains the condition is less than 2.45. So here the out of 150 instances that are 50 elements are less than this condition, that is less than 2.45, and all the remaining 100 elements are greater than the condition of 2.45. Okay, this is the less than 2.45 and greater than 2.45. Okay, so this so totally 100 elements are belonging to greater than the 2.45 elements. Now out of 100 these elements, 54 elements have the we are checking the other condition. That is the condition equal to petal width. Out of this 100 samples, so 54 elements are 54 elements are less than the petal width of 1.75, and 46 elements are greater than the petal width of 1.75. Okay, so now a node value attribute tells you how many training instances of each class this node contains. Okay, now for example at the bottom right node, so this is the bottom right node. It contains 0 setosa and 1 iris colors and 1 iris versicolor and 45 are belonging to iris virginica. That means here out of 46 elements, so those elements are belonging to 0 element belonging to setosa, 1 element belonging to versicolor, and 45 belongs to versicolor. Virginica. These are called as setosa, and this is belonging to versicolor, and this is belonging to 45 belongs to virginica. Okay, now. So here the condition is petal width is greater than 1.75. Okay. So like this, we are going to find out the corresponding class labels. So here majority class belongs to virginica. Why? The 45 elements are out of 46, 45 elements are belonging to virginica. That's why the class label is assigned for this one is virginica only. Okay. Now finally a node's Gini attribute measures its impurity. So a node is pure. That means when we can say the node is pure if it is a Gini equal to 0. Otherwise that node is called as a impurity node. Okay, so if all the training instances it applies to belong to the same class, then that is called as a pure node. So here, for example, at the depth 1, the left node applies to all are belonging to iris setosa, the training instance. Okay, suppose here, for example, here the condition is petal length is less than equal to 2.45. That means the condition satisfied elements are 50 elements are there. Okay, out of all the 50 elements are belonging to same class only. That means the Gini equal to 0.0. That means here all the training instances are belonging to same class only. Okay, that is the main importance of the pure. If the Gini equal to 0.00, that means we cannot split the further. That's the main purpose of the Gini value or pure node. Okay, if it is a node is a pure node, we cannot further split that into different levels. So suppose the Gini equal to some other value, then we can apply the we can further going to split the data. Okay, now it is a pure node and its Gini score equal to 0. Okay, now here we are going to use some formula to find out the Gini value, Gini score of Gi of the ith node equal to Gi equal to 1 minus sigma k equal to 1 to n p square of ith and k element. Okay, G equal to 1 minus sigma of I equal to 1 to n p I square or the probability of score equal to corresponding element to corresponding k column. Okay, so this is about the Gini index value, Gini impurity value. Now in this equation, Pik is the ratio of class k instances among the training instance in the corresponding ith node. So for example, here the depth of the 2, so this is the depth 0, depth 1 and depth 2. The depth 2, the left node is this one. Okay, the left node is this one. So here at this node, the Gini score equal to the 1 minus of here it contains 54 elements. The total number of elements are 54, and out of 54 elements are 0 belongs to one class and 40 belongs to one class and 5 belongs to one class. So here 0 by the 54, the total number of elements are 54 whole square minus and 49 by and corresponding total number of elements are 54 whole square and the minus of 5 by 54 whole square. So that is equivalent to, if you apply the equation, okay, then equal to, that is equal to 0.168. So that is the Gini value of the corresponding variable or corresponding node. Okay, that means here some elements are misclassified as a versicolor. So out of 54 elements, 49 elements are belong to one class and 5 elements are belong to other class. So based on that information, we are getting a Gini value equal to 0.168. If you apply the maximum depth to one more level, so increase the maximum depth equal to one more level, automatically we can further split the data into two classes. Okay. Now, scikit-learn uses the CART algorithm which produces the binary trees. Okay, non-leaf node always have the two children. Okay, that means yes or no answers like questions. Okay, so here using the CART algorithm, scikit-learn is the default one is scikit-learn uses the CART algorithm and it produces the binary tree only. Okay, either is a like writer. Okay, two children only, whether is a true or false like that condition. Okay, so internally it uses the Gini value, Gini as a criterion. And however, other algorithms like ID3 can produce the decision trees with the nodes that have more than two children. So for example, here this is a root node and it contains more than two children. Okay, more than two children. Like that, we are going to construct the decision tree with the help of ID3. But whereas here in the CART algorithm, we are using the only binary tree only. So now, for example, here the decision tree boundaries are the thick vertical line. Here the thick vertical line, that is petal length is at 2.45 that exactly divide the data into two parts. The depth 0 and the depth 0. Okay, all are belonging to setosa, and here is a combination of versicolor and virginica. Okay, now since the left area is pure, that means only all the elements are belonging to same class only. Okay, so it cannot be split the further any way. Okay, whereas coming to right hand side, so here combination of sepal and combination of iris versicolor and iris virginica. Okay, there is a impurity is there, so we can apply further splitting the process. So how your right hand is there is a impure one, so the depth 1 at the depth 1 the right node splits at the petal width equal to at the petal width equal to 1.75. We can represent the data into dashed lines. Okay, here the dashed line that divided into two parts once again. Okay, so at the max depth it was set to 2 and the decision to stop at this right here. Okay, this is the right we can stop the process. If they set the maximum depth equal to, then the depth 2 nodes would be added to another decision boundary. Okay, like these dot lines. Okay, these are dot lines. We can further split the process into two things. So like that we are going to consider decision tree. So here the decision tree boundaries are, the first boundary is the petal length is less than or equal to 2.45. The divide data into two parts. Okay, all are belonging to the left side. This one is belonging to setosa and right side belonging to two classes. Is combination of iris versicolor and iris virginica. Okay, now we are going to further boundary at the depth 1. The petal width equal to 1.75. So the divide data into iris versicolor and iris virginica. Okay, now if this would be how then divided further for classes, if max depth was set to 3, then that divide into 3 parts once again. Okay, so like that we are going to consider the decision tree and making the predictions of the corresponding class labels of the given data. In the next class, I am going to explain about the estimating the class probability of a given data. Okay, thank you for watching our video. If you like the video, please subscribe my channel. Thank you.